And our first speaker for this session will be Nate Mantua, who will be speaking on climate influences in Puget Sound. You go.
Yeah, so this next session for three speakers really focuses on the abiotic processes, and a little different from our previous workshop is that we're thinking broadly about this, so not just marine indicators, but also in terms of freshwater indicators as well. So we're going to have several talks starting with climate and Nate Mantua.
Okay, I've been trained on the technology. Let's see if I can pull it off. I've been asked to talk about how climate influences Puget Sound and trying to hone in on some potential indicators from the abiotic environment that could inform the forecast. And like Richard did on Monday in his really terrific overview talk, I'm going to start from sort of big picture and thinking first about the primary seasonal evolution of the typical year. Really every year undergoes some variation that includes a winter climate that has lots of storminess, and the North Pacific is dominated by low pressure. There is an area of high pressure parked off the coast of California and Baja that's pretty small, and each of these lines are contour lines of atmospheric sea level pressure. The arrows are meant to indicate the surface wind field that goes with that. So we have lots of winter storms developing in the North Pacific and tracking from west to east into our neighborhood. And this typically begins in October. It did dramatically this year. I think October 12th, we went from the drought, something like the drought of the century, to a wet spell that ended, I think, yesterday. But it leaves this imprint of low pressure, and it leaves this circulation pattern that dominates, that for our part of the world brings in south-southwesterly winds along the coast, and that causes Ekman transports toward the shore. It brings warm, mild air into our part of the world, and it brings in tremendous amounts of precipitation that either run off in warm watersheds or collected snow in the colder places. And there's this dramatic shift in the circulation of the North Pacific in summer, and this can happen typically in the spring, around mid-April is common, to see the North Pacific high become the dominant feature, where it intensifies, it expands northward, and it produces very strong winds from north to south, especially in northern California and southern Oregon, and then that wind influence off the coast of Washington and Vancouver Island is not nearly as consistent, and it's sort of intermittent weak winds are the average condition, and sometimes we have south winds with summer storms, and sometimes north winds with fair weather, but the upline itself off the coast is driven by winds is relatively weak compared to lower latitudes. And of course we have a lot drier weather in summer with that North Pacific high blocking storms from coming into our part of the world. If we look at the seasonal cycle of precipitation based on 30 years of data, this is for the Puget Sound lowlands, October through September. The precipitation peaks in November and December and January. It slowly diminishes. We finally see the sun in July and August. Sometimes it lingers into September. It's minimum season. This topographic map indicates the terrain around the Sailor Sea, the white areas being the high peaks. The black areas are near sea level. Those are the river valleys. So you can see, for instance, the Skagit River Valley here, this deep cut in the North Cascades, the Fraser River Canyon here, just to the north. Because of the variations in topography and the microclimates that causes, and also the change in the distance to the ocean, we have very different hydrologic regimes, even under the same precipitation climate. So the Skagit River, these are 30-year averages of the daily flows in the Skagit River, again from October to September. And you see that flows typically build October into November and December, then they actually moderate on average. And there's a seasonal minima that is happening in about March and early April, and then they run up again as you get into May and June, with snowmelt being the dominant contributor there. And then a low flow season that's typically in August and September. The Puyallup River coming off of a warmer watershed off the flanks of Mount Rainier, it actually has three peaks in this hydrograph. One that first comes in around November, another one in February. You see the coldest part of the year just dips down a bit because you start to have a greater contribution of snow accumulation and less runoff. And then another springtime minima, and then a build up to a late spring, early summer snowmelt peak. Here's a Skokomish River that comes off of relatively warm watersheds on the south flanks of the Olympic Mountains. And it's almost totally rainfall dominant. There's a little bit of a dip there in this climatology, indicating that there's a little bit of snow that's accumulating there, but mostly when it gets a storm there, it's rain, it runs off. So you have these very different patterns of runoff, and that's important for the different patterns of freshwater inflow into the Sound that are structuring a lot of the subbasins. If you look at the monthly mean river discharge from different watersheds, and I think we saw a picture just like this on Monday from Richard. But here's the Skagit River, the biggest river in Puget Sound, and again it's got its double peak hydrograph. Now we're going from January to December here, sorry for flipping the scales. Other major rivers, the Nooksack, the Puyallup, you sort of add these all up, and you account for most of the watersheds in Puget Sound, and you see that the bulk of the flow comes in these two peaks, one in midwinter, and then a second one in late spring and early summer, and then very low inflows, typically in August, September, and early October. So strong seasonality, but the seasonality differs by subbasin again. And then the Fraser River, which is the biggest source of fresh water into the Salish Sea, has a very sharp peak in June. It's a much colder watershed, draining big area in interior British Columbia. Very low flows, typically in winter. And of course, you can have warm storms, though, in the wintertime that deliver massive freshets and floods in the Salish Sea. And that happens typically from October all the way through February, typically. Again, going out to the coast, the other sort of boundary condition for Puget Sound, so you've got the freshwater inflow, you've got direct atmospheric forcing, and then you've got what comes in through the Strait of Juan de Fuca. And that seasonal variation and upwelling, and then the intermittent variability in winds that drives variability in upwelling is really critical for what feeds in the deeper waters, the inflows into the Strait of Juan de Fuca that eventually make their way into the Salish Sea. You can also have intense winter storms with very strong south-southwesterly winds causing strong excrement transports and inflows of oceanic water into the Sound in the wintertime. So you can reverse the estuarine flow in big storm situations just from intense wind events that are piling up water, driving that circulation back into the Sound and sort of reversing the estuary behavior. What I want to talk about next is results from a couple of studies that I was involved in that were really aimed at forecasting harmful algal bloom risks in Puget Sound, but the salmon problem has a lot of the same challenges associated with it, and the lead on this is a woman at the Northwest Fisheries Science Center, Stephanie Moore, and she's done a lot of good work in this area. But what we had set out to do was to collect as much of the physical oceanographic data that we could get our hands on to document, describe space-time patterns of the seasonal, the interannual, and the interdecadal variations in the water properties of Puget Sound, and then to link that variability with climate indicators at various scales. Local influences, things like the freshwater inflows in various river basins, temperature in the atmosphere, precipitation, then go into larger scales, things like coastal upwelling, and then to even larger scales like the PDO index, the NPGO index, the Aleutian low forcing, things that we had heard about on Monday. So I'm going to take you through some of the results of that work and point out that there have been some really nice data collections that have been sustained over a number of years now. And one of the sources is Washington's Department of Ecology. They have a marine waters monitoring program, and they began an intensive sampling program at 16 stations in the early 90s. For this study, we looked at the period from 1993 to 2002, where they had profiles that were taken out of float planes regularly, just one per month though, which is one limitation of the data set. And that was an important part of our data set. The University of Washington has a PRISM program where they have been doing twice a year transects through Puget Sound, its major subbasins, and then out through the Strait of Juan de Fuca, looking at both the physical oceanography and also some of the biological oceanography. And then there's some longer records that we've been really interested in looking at because it extends our understanding of the time variability. And a lot of the longest records come from lighthouse stations in British Columbia, and I'll talk a lot about Race Rocks because it turns out Race Rocks is a really good indicator site for some of the patterns we see within Puget Sound. The USGS has stream gauge data networked around major watersheds in Puget Sound. Some of them go back to the early 1900s. NOAA's Pacific Fisheries Environmental Lab has an upwelling index database that they have maintained and update all the time for the Pacific coast of North America. And there are some other climate data sets that we used in this study, and I'll talk about most of those. And just to give you a little bit of context for what the Department of Ecology marine waters monitoring stations look like, they have sites, you can't really make it out, I guess, in this chart, but in the subbasins, sort of out here in Admiralty Inlet, in the Whidbey Basin, the central part of Puget Sound, South Sound, also a couple at Hood Canal, and then one up in the southern end of the Georgia Strait. And here's the map of the transects that the PRISM crews take, also up in the Whidbey Basin. And this set of maps looks at climatologies based on the vertical profiles from the Department of Ecology's sampling program from those 16 different stations. And I just want to draw your attention to a couple of these. First, the way that this is plotted, it goes from the surface down to a depth indicated here. So in this case, in the Admiralty Inlet, from the surface down to 60 meters depth. And from the left side is January, to the right is December, so this is averaged over the 1993 to 2002 period. And these are temperatures in the water column. And the blues are the cold temperatures, I think around 8 degrees centigrade. What you see here is very little seasonal variability. There is a bit of warming that extends to a depth of about 30 meters in mid and late summer, up to about 10 degrees centigrade. And you can compare that with a place like Oak Harbor, where it's a lot shallower, just 0 to 10 meters here, much stronger seasonal warming. That gets up to about 16 degrees. That's with the warmest colors there. Places like Hood Canal also have a lot more shallow warming in midsummer. So we're at 12, 14, 16, even 18 degrees centigrade when you get into August, early September. So depending on where you are in the sound, you have very different seasonality, and that's because of how well it stratifies and how much mixing and flushing goes on there. Is it close to a place with one of these intense mixing zones over the sills, like Abiotic Inlet? Well, there you see very little in the way of seasonal variation. If you're in a subbasin that stratifies, you can get lots of warming, and some of it in some places can extend to a depth of 10 meters. In some places like this canal, it can be very shallow and just be trapped in the top few meters of the water column. This is the same kind of information, but now for salinity. And think about the seasonal pattern of surface freshening that comes with the river flows into the sound. So here is, again, Abiotic Inlet, and you see almost no seasonal variation in the salinity from the surface down to a depth of 60 meters. In fact, there's a little bit of a peak of high salinity late in the year, but very little signature of salinity change in the surface waters. You look at the Whidbey Basin, and you see freshening happening January through July, and then again, it's freshening there in the shallow surface waters in November and December. So here you have big rivers like the Skagit and the Stillaguamish dumping large amounts of fresh water in all months except really August and September. And somewhere like Hood Canal, you have rivers like the Skokomish putting most of their fresh water into the system in the winter time because they don't have a snowmelt peak. So you see that sort of blue spot in the upper few meters just early in the year. So again, large differences depending on where you are, which subbasin you're in the seasonal pattern, simply because they're draining different watershed types, and the flushing that happens there can be very different, and the vertical mixing through tidal action. So what we did is we took those profiles that exist for that 10-year period, and we subjected them to a principal components analysis because we wanted to see, are there patterns shared among these different sites in terms of the seasonal and interannual variability. Again, there's just 10 years of data here, not a lot of data to draw out variations, but what we found turned out to be pretty nice results because there is one simple pattern that stands out in the temperature profiles, in the salinity profiles, and also in density profiles that you create from the combination of temperature and salinity. And they are common variations from the surface to depth at every station. It's as if Puget Sound warms as a whole or cools as a whole over the course of the year, from the surface down to the depths that we looked at, limiting really to the upper 80 or 60 meters in this analysis. Same is true for salinity, that there is a salinity pattern that if the sound was fresh, that freshening occurred at all stations. And the density profiles also basically shifted back and forth at all stations in concert. And these patterns, the temperature pattern explains about 42% of the variance at the 16 different stations. Salinity was even sort of more compressed in this pattern, 58% in density, which is dominated by salinity variations. Is about the same as salinity. These time series represent that Puget Sound-wide pattern for temperature, salinity, and density. So that temperature pattern from 1993 to 2002 shows relatively warm years in the early 90s, cold periods here in the sort of, I think that's 97, 90, let's see. Actually, that's 95, 96, and then a warm period of 97 and 98, and then some colder years for the rest of the record. Salinity was not correlated with temperature, and you can see the sort of fresh period in the late 90s, early 2000s. There was a big drought year in 2001 that showed up as a salinity spike. And this maximum buoyancy frequency, a measure of the stratification of the sound, showed relatively high stratification in these low salinity years, low stratification in the high salinity years. But with that relatively short record, we would have a really hard time saying something about correlations to large-scale patterns. We just have a few ups and downs in the time series, very few degrees of freedom. so we were seeking ways to bridge that into a longer history. And we looked at some of these lighthouse data stations and found that race rocks was especially well correlated in terms of the sea surface temperature with the temperature pattern and the salinity, again taken to the surface with this salinity pattern. And here the correlations were broken out by season for the temperature pattern, highest in the winter, but still high in spring and in fall. The weakest correlation between the race rock pattern and our Puget Sound pattern was in summertime, but still positive. And then for salinity, the highest correlations were spring, summer, and fall, but still high in the winter. These stars are indicating the degrees of statistical significance, so 3 stars is 99%, 2 is 95. So we're using the salinity and the temperature at race rocks as this indicator site for the Puget Sound pattern as a whole. And I showed this on Monday. You break out the observations at race rocks by month and year. So here from January to December, from 1921 up to 2011 on this graphic, you see that salinity doesn't really have any kind of clear pattern through time. You can pick out periods with relatively low salinity, like here in the late 90s, this 2001 year, the drought year, with sort of a red stripe across. The 80s tended to have higher salinity than the 90s as a whole. You see periods in the 40s with relatively high salinity. If you look at temperature, it seems a little bit easier to interpret, to me at least, that you see these warm eras that really stand out, these brighter red colors in summertime months in the late 30s and early 40s, the late 50s, early 60s, and then the period from 1982 all the way up to 2009 being especially warm throughout the summer periods. And you see the blues also fade, indicating that the winters were not as cold as they were, say, in the late 80s in that case, but especially the 70s and some of the years in the 50s and 40s. And another way to look at just the temperature history is to look at the annual average calculated for each year. And now maybe it's a little bit easier to see this kind of variability in time with warm eras early in the record, another sort of brief warm period, some cold years in the early 70s, warm years, especially in the 80s and the 90s. And overall, there is an upward trend. And if you drew a trend line through this, you get something like a half or 3/4 of a degree centigrade warmer than average, warming over the course of the record. And then the El Nino years really stand out as the big spikes. Big El Nino years stand out as especially warm in the record. So then, getting to indicators that are driving that variability in the temperature and the salinity, we did a bunch of correlations. And sorry for showing you a correlation table, but the words over here summarize the key points. Skagit River stream flow was the best thing correlated with the salinity in winter, spring, and summer. And in the summertime, salinity was also correlated with the upwelling wind index of the coast. So you're starting to see a diminishment of the freshwater influence in summer, and that's the peak upwelling season, so that sort of makes sense. Sea surface temperature was most correlated with the regional air temperature in all seasons, but during the wintertime, the large-scale indices for the PDO, for the Aleutian low, for ENSO also were correlated, but not that strongly, only at a level of about 0.5 to 0.6. And this is another graphic that was shown a couple times on Monday from the Georgia Basin, which has a monitoring station with twice per month samples from the surface down to 400 meters from 1970 here to 2007. And what they showed here was that the variability in temperature in the Georgia Strait was coherent from the surface all the way down to 400 meters depth. And that it has also strong correlations with ENSO, some of those really bright stripes are the big El Nino years, the big blue stripes are La Nina years. And that these correlations were also well correlated, the temperature is well correlated with the sea surface temperature in the whole of the Northeast Pacific. Line P, for instance, off the west coast of Vancouver Island, its variability well correlated with what you see in the Georgia Basin. And just thinking about what's coming up for us in the future. You know, the group that I work with at UW has done a lot of work summarizing IPCC model results for the region and trying to downscale it, bring it down to Puget Sound, Western Washington, and other parts of the Northwest. And I just summarized some of these key findings that we've had. The climate models from this recent the latest generation that are available, there's a new set coming out right now though. Air temperature is expected to change by 1 to 6 degrees centigrade over the next century. Over the past century, in our part of the world, we have a warming trend of about 0.8 of a degree centigrade. So this is suggesting at least as much warming, perhaps a whole lot more, like 8 times more within that family of scenarios. And from what I've seen from this next set of model results that will be reported next year by the IPCC, that range is not expected to change very much. It's still the sort of 1 to 6 degrees centigrade for our part of the world. Precipitation trends that come out of these climate models are actually all over the map for the Northwest. There's no clear indication. There is a tendency for the models to have more precipitation in winter and less in summer, but different models have very different outcomes. So talk about uncertainty. It's not that different from the uncertainty we've lived with for a long time. That is it going to rain more or less this winter? Not a lot of information, except with our ability to keep track of El Nino and perhaps TDO and that influence over the next year, too. The consequences of a warming climate, though, are pretty clear that we can expect snow lines to rise, and that as snow lines rise, we would also see a shift in the timing of stream flow and runoff in those watersheds. And a really interesting thing about the climate that we've been living in for the last century is that in the Puget Sound Basin, on Vancouver Island, Georgia Basin, we have a lot of these watersheds that collect some snow and generate runoff from rain when it's warm enough. They're transitional. They're very sensitive. A little bit of warming can have a big shift in the timing of the delivery of water. What that means is more water in winter and early spring, less water in late spring and early summer. Think about consequences for cold water fish, longer low flow periods in summer, probably lower low flow periods in summer. And the modeling work that people like Alan Hammond have done show that you also get big changes in peak flows during the fall and winter. That just making those basins more rain dominant means that you can generate bigger floods. And the scenarios we've looked at show some substantial increases in the magnitude of things like the 100-year flood, or a big increase in the frequency of what we thought was the 100-year flood. Interpret it that way as well. The climate models are showing no clear indication for changes, any systematic changes in summertime upwelling winds. There have been individual studies that look at individual models that say, oh, yeah, upwelling is going to change. But when you look at 20 different climate models run multiple times, you start to see that they're all over the place. There's no strong tendency for more upwelling in the summer or less. So that will also be critical for the structuring of the coastal ocean and that influence of what comes in from the Northeast Pacific into the Strait of Juan de Fuca. You know, how that plays out. And looking historically, the people I've been collaborating with have shown that there's lots of variability, interannual, interdecadal variability in summertime upwelling winds. And good evidence, as we saw from the morning talks, is that has some influence on ocean conditions according for salmon. But the warming is likely to be surface intensified because the atmosphere is warming first and it's pumping heat into the ocean. So that would tend to increase stratification. That's especially true out on the coast, and probably especially true in places that already today seasonally stratify in summer. And where you have intense tidal mixing, maybe that won't be an issue, but the whole water column will then warm by a relatively small amount. And they don't have ocean acidification listed on this, but of course that's another clear sort of present threat from the changing climate. And then this is my last slide. A good thing about Puget Sound, I think, is this pattern that we see, the sort of sound-wide warming and cooling, the sound-wide freshening or getting saltier. That's pretty robust. In spite of the diversity of conditions that you find around the watershed, Puget Sound is relatively small compared to the scales of atmospheric forcing that shape our climate. So we can have individual storms where you get a flood in the Skagit but not in the Puyallup. But over the course of the whole winter, typically if we have above average snowpack and precipitation in the Puget Sound Basin, you see that everywhere in the basin. It's not like the North Sound gets a drought while the South Sound gets big flood. Temperature is even more spatially correlated than precipitation. That again, the scale of the atmospheric sort of imprint over the region is much larger than the scale of the Salish Sea. We tend to have pretty large scales. It's especially true in winter, but it's also true in summer. On Monday, we saw that the NPGO, this is another major pattern in the Northeast Pacific, it structures a lot of the salinity and the nutrient field in the Northeast Pacific, and that is important for the deeper inflows to Puget Sound. But I was looking at this last night. For the surface waters, it's just not correlated. That it's these local forcings, the wind in the summer, but the stream flow in most of the year, that's really driving salinity variations within the sound. And this ENSO, PDO, the Aleutian Low, those are most important in the wintertime in shaping what happens in the sound, but they also carry over for about 3 seasons. That you see the imprint of ENSO lasting into spring and summer in most years. It doesn't just happen in the winter and go away. It shapes the evolution of what happens in the coastal zone and in the sound for most of the year. And then we have this warming trend that we have in Race Rocks, and one of the points we have made in our paper is that all that data collected in the 1990s and early 2000s and now the subsequent data has mostly been concentrated in a period where the sound's really warm compared to where it's been for most of the last century. So short time series, it's easy to get fooled about what the state of the world is. So trying to get that longer context is helpful to understand what's the variability and how can it play out. So that's all I have.
Next up is Martin Liermann to talk about freshwater processing. When I originally organized this, I had asked George Pest to present this, and he is now buried in the legal discovery process, and so Martin has graciously offered to stand in for George. So with that, I'd like to turn it over to you and go from there.
Click on this to advance it.
I think so, yes. Pay attention to Laura. We won't give you time.
Okay, great. Well, this was originally George's talk. He's about 3/4 of the way through, and I'm sure it was a fantastic talk. Then I showed up and started monkeying around with it and trying to turn it to my own. So any confusion is probably due to that process. Just an overview. I'm going to talk about some freshwater drivers and sort of and how they affect temporal and spatial variability in adult recruits. It's going to be sort of an overview with just a couple of examples, and not talk about certainly the multitude of different freshwater metrics that are out there. Talk about how those patterns reflect a complex interaction of environment and biological processes, and show that what's important can change over time. I think that's a theme that's sort of been reoccurring in this morning at least. And then at the end, just add a little bit of my statistical background and encourage some skepticism when it comes to looking at, to encourage a little skepticism when looking at some of these processes or these the evidence. So, this is data that George collected collated for his dissertation, looking at Fraser River pink salmon. And on the triangles with the dashed line, that's the population above Hell's Gate. It was cut off prior to 1947 due to landslide associated with a railway. And then the dark, the squares with the solid line, that represents sort of the general North American pink population over time. And you can see that for the first period here, sort of from the mid-40s to the mid-60s, there's sort of a decreasing trend in the North American population, while there's an increasing trend in the Hell's Gate population as it expands into this newly available habitat. So here's really what's driving this population is the expansion of habitat. There's more habitat. In the second period, the population is doing much in particular, perhaps responding to smaller ocean signals, and then from sort of the mid-70s on, there was a pretty dramatic increase in both the sort of the overall North American pink population and the one above Hell's Gate. And if you look at these three red circles, they represent three different flows. So getting past Hell's Gate, even after they fix things, is still difficult, especially in high flow years. And these represent three pretty dramatically different years in terms of flow. So the higher point there was when the flows were lower and it was easier for the things to get past, and the lowest one was particularly high flow where it was difficult. So again, there's a number of different things that are driving the returns over time, not just a single metric. So I'm going to talk about the two metrics I'm going to talk about, sort of focus on this are first looking at a metric of habitat capacity, and then also looking at peak flows and how they might affect returns. So the first one's looking at sort of trying to explain spatial variability in recruitment. The other one's trying to explain some temporal variability. But again, this is just these two specific examples. So in the first one, there can be difficulties in trying to figure out what the capacity of your population could be. And that could be just because you don't have any data, any escapement data at all for that population, and that's the case of a number of Chinook populations up in BC, for example. Or if you do have spawner recruit data, as a number of people have commented, it tends to be very uninformative, and it's difficult to get some idea of what the capacity should be for that population. So Chuck Parkin and a number of his colleagues at the DFO collected a number of data sets and brought them together and found for Chinook populations, which they thought were relatively high quality, and they would be able to get decent estimates of sort of some population dynamic parameter like equilibrium population size or MSY. And then they compared those values they got to metrics from those specific watersheds. So they had things like discharge, and here I have acceptable watershed sizes, which they eventually settled on. And it had to be something that was readily available for the watersheds they were interested in. So they, a lot of the more detailed things that might have worked better, wouldn't be appropriate in this situation. And you can see that, at least if you look at the log scale, that there's a pretty tight relationship between the accessible watershed area and the equilibrium population size as predicted by the spawner recruit data. And that you'd also expect to see, more, ocean type, Chinook for a given size watershed. So, how could you use something like this? Well, this is just, one example. The Elwha River, as I'm sure most of you know, they just, the process of, removing the last of the two dams. And, the dams have been there for a long time, and the historical data wasn't very good, so we didn't know, how many fish to really expect, what the capacity of Chinook should be for that basin. And so we just, we used an equation straight from the report that Chuck and others put together, and we came up with a rough estimate of, maybe 5,000 stream type and 10,000 ocean type Chinook. This is George slide. If it'd been mine, there would have been, big distributions around those. But okay, so that was looking at sort of trying to explain difference, in spatial variability in recruitment, and this one's more looking at temporal variability in recruitment. This is a study of the collaboration between Chris Johnson and with WSW and Phil Roney at our center at NOAA, and with a number of other people, and they did a very involved project. They constructed like per year maybe 80 artificial reds over maybe 70 miles in the upper Yakima, and to get some idea of spatial variability in egg-to-fry survival. And what they found was, in the first year they looked at it, that survival was high, and there wasn't a lot of spatial variability in that they saw in this, which was sort of a surprise to them. And when you looked at things like the amount of fines they found in the artificial red compared to survival, you didn't see much of a relationship. But one thing that they did see, they were able to, it did explain quite a bit of variability, was the parental cross they used. These were hatchery fish, and they had control over, which fish they crossed with which ones, and they did it in a way so that it wouldn't be confounded with space or the location. So that was the first year that they did this, the first winter they did this, and it was, one thing unique about this year was it was the lowest peak flow in history, in recorded history in the last 100 years. So it was like 2,000 CFS. So the next year, it was about 8 times that, and things were different. So now you can see there's quite a bit more spatial variability in the egg-to-fry survival, as measured by the experiment, and that when you added those points, these squares here, to the relationship between fines and survival, you can see that now you're starting to see at least a hint of a relationship between those two. So this is sort of another example of how what's important can change pretty dramatically from one year to the next year. So here's another example of looking at peak flows, but in a different context. This is the Skagit River, and Eric will have to correct me and get up here if I'm making a big mistake. But the basic idea is, the egg-to-fry survival is can be affected by a scour, fine sediment intrusion, and then organics that are going to result in the loss of oxygen, and that these can be caused by peak flows, which are due to things like increased precipitation and road density and other land use. So in a basin below the Skagit or the north fork of the Squamish, they plotted the annual maximum discharge over time, and you can see right here that there's a pretty clear increase in that, and that they thought, well, let's break it into a few different. And again, this is work that Robin Wakel, Tim, and George did. They broke it into 3 different periods, and those periods are represented here in this plot of a recurrence interval versus the discharge, and you can see that what used to be a relatively infrequent flow, so maybe like 800 CFS for the green line there, is now relatively common, almost just a regular seasonal bankful flow. And if you combine that with information, and here this is some of the data, looking at the relationship between egg-to-fry survival or egg-to-fry out micrant survival, and look at that versus flood recurrence interval, you can see obviously that there appears to be a negative relationship here, and if you can combine that with the information on what was happening in terms of changes in flood recurrence interval, you can see that would have a pretty dramatic effect on egg-to-fry survival depending on which period you were in. Now, we're combining data from the Skagit with the North Fork still a Guamich, but still I think that sort of gives you an idea of sort of the magnitude of effect that you might expect over time. So to end, since I'm a statistician, I just had to add this little bit here, and people have already been talking about this to some degree. Just that we look at a lot of patterns, and in our field in particular, we're stuck with data that really isn't that great in terms of from a statistical perspective. And just to sort of illustrate this, I've plotted 16 plots here, and these are generated completely at random. So there's no relationship between X and Y in terms of the process I use to generate this. But we're great at seeing patterns, and so you start adding lines to this, and you can, if you allow for nonlinearity and you start picking through a bunch of variables, it's really easy to see things, and you start saying, oh, well, you see those points there, that was, I know what's happened that year, it's easy to come up with convincing relationships, and I as a statistician, I still, catch myself, doing this all the time. And I think that, one of the problems we face is that we tend to have first small n, so not a lot of data. And to exacerbate that, a lot of our data has autocorrelation. So things that are close together in space tend to be more similar, and things that are close together in time tend to be more similar. And that takes the effective population size and reduces it dramatically. Say from 20 years of data, now you really have maybe effectively 10 years of data. What we do is tends to not be repeatable, so you can't just repeat the last 20 years. Like, for a drug trial, they can, do that drug trial, get a result, and they're not comfortable, so they can repeat it. We don't have that luxury. So it's hard to corroborate, the results. We tend to have small effect sizes, smaller squares, small effect sizes, and very noisy data. We look at, there's just, lots and lots of, potential covariates and different models we can explore, and we're really good at coming up with plausible explanations for patterns that we see. And on top of that, you have, because, our area is, there's been a lot of money going and a lot of interest going into it, a lot of people are looking at these patterns, and, most of us don't publish, results that are, don't show some kind of, something interesting. So that means there's this sort of large-scale collective data dredging that's going on. People are looking at all sorts of different, ways of trying to explain things, and the people that find interesting patterns publish, but they don't count for that in their publication, right? They can't. They don't know what other people have done in the past. And this isn't unique to our field, but this Roach told me how to pronounce his name. It's like Unides or something like that. Apparently Yanni would be his name in Greek. But so this is sort of an idea that's been around for a while now. That a lot of, it's not just that a few studies are wrong. It's that a lot, maybe the majority of the studies are reporting results that are probably incorrect. And people started trying to, for example, repeat medical studies that they were developing new drugs and things like that. And the drug companies were finding that it was only maybe 1 in 5 or 1 in 10 that they could actually replicate the results that people had published. They'd used statistics, had gone through the review process, and who knows where we fall as a group in that. But I think that it's certainly the case that a lot of what we publish isn't true. So what you have to have some kind of something to say about it. What do we do about it? I think one of the main things is just to be skeptical. There's a lot of results out there already, and it's good to when you're looking at things, be skeptical of those. I think that one of the things that we suffer from as well, because we can't sort of repeat the same time period over and over again, is that we think we're looking at different data, but we're really looking at sort of the same data. That a lot of the data we're looking at is correlated, so it might appear to be corroboration of a study, might just be sort of looking at about the same thing. Okay, now we're looking at survival based on hatchery data, but we expect that to be correlated with that other metric of survival that we were comparing the PDO to before, or something like that. Watch out, in particular be concerned when you see small sample sizes and models of many covariates. Try to account for, model uncertainty when you can, but recognize that that's not going to be enough, that still there's going to be results that get through. Try and leverage larger data sets, saying if you show a relationship in one basin, try and, see if you can see a general pattern across multiple basins using meta-analyses. And just use your biological knowledge, which it seems like people are doing. And this isn't sort of a critique of what I've seen today. It seems like, people are well aware of this problem and doing their best to avoid it. But I think, because I'm a statistician, I see myself falling into this trap all the time. I know it certainly must be the case that that's true for, others in the field as well. So in conclusion, I guess there's a lot of freshwater factors out there. We just looked at just sort of illustrated a couple of them that can affect returns, and that you would expect that freshwater capacity would vary by watershed, but you might be able to find some metrics that would explain that. I think that sort of the larger point is that what's important can certainly change across time, and that the biological factors such as parental fitness can induce substantial variability. All I'm finally I just covered sort of be skeptical and sort of keep that in the back of your mind as you're looking at your results and producing results. Thanks.
Thanks, Martin. Our third speaker for the session is Eric Beamer from the Skagit River System Cooperative. We'll be talking about environmental predictors in the estuary.
So, I think in the handout it says estuarine processes, and I'm definitely not. What's that? Yeah. Definitely not going to give you a primer on estuarine processes. I know Corey asked me to talk because one, I work with them a lot, but two, we started working in the Skagit estuary back in 1995 to try to figure out some basic ecology of the Chinook salmon, as well as test the hypothesis of whether there's density dependence occurring there. And as a result, we ended up measuring some environmental conditions along with the fish, mostly to understand sort of what we thought was habitat suitability. But those data now, 95 was a long time ago for fish sort of environmental data, so those results may be useful in sort of thinking forward about these ecological indicators. So Corey's the co-author, and he might be sort of the one that keeps me a skeptic or not finding false correlations. And I used some data from Kim Larson, who I've worked with at USGS on otoliths, and then also David Teal with some genetic marker capture sort of results for growth rate. So that's where we're there. Where we're talking, excuse me, I have to turn my head because I just don't know what's necessarily coming out here. Anyway, it's a workshop, and you can just say stupid stuff on the workshop. So our estuary, our natal estuary, this area, it's a tidal delta. geomorphically, and then the rest of our sort of estuary is bounded in red, obviously part of the Puget Sound, part of the Whidbey Basin, which is part of the Puget Sound. We're going to talk within the tidal delta, really sort of these three wetland zones, an estuarine emergent marsh zone, and an estuarine scrub shrub zone, and then a riverine tidal zone. I didn't have a good picture for the scrub shrub zone, but they're very, very different habitats. And of course, I think this was shown earlier in the week, big changes in wetland area and fragmentation over time. We're also out in Skagit Bay uncovering some what we call nearshore or some shoreline areas, fish living along the shore in open areas, as well as these lagoonal systems we call them pocket estuaries. So they were sort of dotted along all over the place in the Whidbey Basin historically. But I know I'm supposed to talk about abiotic things, but for me it starts out with the fish. And I think Kurt showed my slide earlier in the week, but basically we see these strong functional relationships within the Skagit estuary and out in Skagit Bay that seem to be indicating their density dependence, both on results with abundance of fish as well as their size. And looking at otoliths, we also see that the length of time fish spend in the tidal delta varies year to year, and even that seems to be explained by the density dependent sort of issues. And yeah, 3 dots, that's really good to get our squares. The only thing that's better is 2 dots. But so it's sort of, what else is left to explain, and tongue-in-cheek, obviously, but, I'm a big advocate that we need to be monitoring the fish, and we can do a better job. We should be keeping track of the fish at appropriate life stage transitions and looking at their size and abundance and that sort of stuff. But there's still some other things to think about, and that's where I think maybe I don't have a smoking gun here as far as what we should be measuring, but maybe there's some things that are influencing the fish that we can think about that are environmental factors that we can think about their fitness further on in their migration. So that's, and there's the framework that I'm kind of thinking about it as. And so we're measuring these abiotic things out in our areas, and they should be influencing the physiological responses of fish as well as behavioral responses and ultimately their performance. But those same things also are influencing the biology of other fish too. And they're all controlled by things bigger than them. And those are all things that have been talked about earlier in the week and even today. But I just want to show some results that relate to individual environmental conditions, and just sort of show how they vary from year to season to even shorter time scales, and then show some slides about how that seems to be influencing what the fish are doing beyond our density studies. So what we're measuring some connectivity in the environment. We're downloading river flow from USGS sites. We're measuring the tides with water surface elevation waters, and then we're measuring things in the water too. And we should probably be measuring some more things. So first of all, habitat connectivity. We started along this trail thinking about it as it's simply a pathway for fish to find habitat. And in the delta, it's really largely the plumbing of the delta, how the channels bifurcate, and where the water goes, which the fish have to use to get to habitat. But locally, once you get to a small channel, it's the depth of that channel and how it couples with the tributary channels. And then out in the bay is where the water moves, so circulation models would be really useful to think about that. So we've done that we've calculated a landscape connectivity index for every blind channel site in the Skagit Delta, as well as the pocket estuaries that are currently existing in our study area. And these results are just showing you that the landscape connectivity is a significant variable year to year. It seems to be different, but it matters each year for the number of fish, the number of Chinook salmon that are using a site over a season. So it seems to be important. Local connectivity, so that's the coupling of the channel to the tributary channel, the blind channel to the tributary channel, and that matters more at a smaller scale. So on a daily basis, we see that helps explain the amount of fish used in the site. So both these things seem to be important. They're both abiotic factors. And you might argue that, well, they don't change that often, but they can change. People can change landscape connectivity through restoration or degradation processes, but they also change naturally. They also grow, and you have channels for both of them. So, but they also, not only does it matter for the fish pathways, it seems, again, we didn't measure migration rates, we sort of infer that just because we know the fish have to swim through the water to get to these habitats. But it also should matter for some of the other environmental variables. And it's logical because not every channel is of the same size and depth, and we're in the same position. And so if you have salt water coming from the bay and river water, fresh water coming from the river, where you're located in the delta is going to somewhat control the salinity you see and how deep that channel is. And it's either coupled or not at a different rate. So you can get water from different sources at different rates of magnitude. So, and in fact, Corey and I did a principal component analysis that did find that these local environmental variations like salinity and temperature did correlate strongly with the measures of connectivity. So just transitioning a short talk, you gotta kind of move on. But anyway, I just wanted to show you some ranges of variability in some of these factors, salinity and temperature, mainly. And I have it organized by the wetland zone. So you can just see there's pretty big variation in the amount of the salinity levels by the wetland zone. And if you go back to the earlier map, the wetland zones really sort of were crude bands of that connectivity factor that I was showing you. So the market mark areas can be highly saline, but they also can be really low saline. The pocket estuaries tend to be the highest, but they are also the most disconnected from the river. Whereas riverine titles, they're always fresh, and scrub areas are intermediate. So there isn't a huge signal and seasonal pattern in this data set. I just lumped a whole bunch of years and a whole bunch of sites just to see that there is some variation. With temperature, you see the strong seasonal variation in each of the wetland zones. And if you look, it's kind of hard with the graph. There is actually some pretty big differences in the seasonal patterns by this type. So, for example, the riverine tidal sites tend to stay lower temperature than the estuarine marsh or merchant marsh and wet, and so on. So there's big, strong seasonal variation, and there's some variation by habitat type. And I'll talk later about why that might be important to this. So, sort of coupling the fish to local environment. So, in our pocket estuaries, this is sort of the average seasonal use of those areas. So, February, March, and April are the big months In some years, it stands out really to zoom that there's a part of the bar there that's shown. In the delta, it's a little bit more protracted, but it still centers around this March and April, and going on all the way back to August. So we think about got this base slide from Dave. If we think about his growth curve that he showed for bioenergetics, and this is for a fish that's a little bigger than what we're seeing. That's about a 95 millimeter Chinook salmon. And as you saw earlier, we're talking about fish that are half that length as they enter the estuary. But our temperature range for the period when fish are using the tidal delta habitat really covers a wide range of temperatures. And for the peak period, it's still a pretty wide range of temperatures. But the fish obviously are going to be working somewhat on the edges of these curves, and if you look at the whole period, you might conclude that there's some temperature influences on growth. Maybe certainly in the beginning, but at the end too, some positive, some negative. And so in our relationships that we did earlier, the density dependent studies, we're not thinking about any of this sort of stuff, but yet temperatures vary quite a bit. And in fact, when we look at fish and look at their growth, these are fish that were captured in specific habitats that we were able to measure their growth rates. They had to at least show 5 or be in those habitats at least for 7 days to account for growth. But we see in the estuarine emergent marsh sort of the highest median growth, but also really, really high variability, and the other sites lower and higher variability. But so maybe there's something to, there's an advantage of being in a warmer habitat, but it can be an advantage and a disadvantage, depending on when that has occurred. So the fact that there's variation and differences in the median values that suggest that maybe we should be keeping track of temperatures more closely and thinking about how these fish may be fit to survive later on. And then just digging in a little bit deeper at the source of variation. So this is just one site within the estuarine emergent marsh zone, and obviously it's showing you something that everybody knows. The tides go in and out, places are flooded and less flooded, but there's a little bit more to the story here. So I have in each of those graphs, there's early, middle, or mid-peak, and a late time period for Chinook use. And I just picked out a 5-day period for each of those periods just to look at salinity and temperature and water surface elevation. So obviously, the top graph, we have lower temperatures, obviously, earlier in the season, and some fluctuating salinity, and the salinity is fluctuating pretty strongly with high tides occurring at the site. And later on, we're still seeing that variable salinity, and it's correlating with high tides, but the temperature is seasonally raised, but still, there's some diurnal fluctuation. But what I want to point out is the dramatic differences, not so much seasonal, but the process. That's sort of a no-brainer, but the processes of how that changes is interesting. I don't have all the figures to show, but Nate showed the hydrograph of the Skagit. And you can see early in the season variable salinity, later in the season low and less variable salinity. Well, later in the season we have the snowmelt occurring in the Skagit, and the bay filled up with fresh water, and so it's suppressing salinity overall and making it smoothing it out, whereas that water's not there earlier in the season. The other thing is, it's interesting how the temperatures, it's not surprising we're going to have an elevated temperature over time. It's spring, it's sunny, it's starting to warm up, but how, despite the diurnal fluctuations are pretty dramatic, and how the water gets hot is interesting. So we have the biggest peaks occur on flood tides during the day, which is contrasting to how the water is cooling on the flood tides during the day earlier in the year. And that's the reason it's different is because this water comes across a dark sand flat as it floods in, and that water, while it might be cool out in the day when it starts, it heats up as it comes in, and by the time it gets to the channel and floods back in, it's quite hot. So the processes that occur, looking just at mean values might not be the right thing within seasons. You might need to be looking at some different things. And I guess I just want to point out there's a lot of variation in these abiotic factors within the seasons. And at the site, I went ahead and sort of calculated this from the level logger data, so it's very robust. There's not much uncertainty. We're counting the measurements every 15 minutes at the site. But if temperature is a limiting factor, I just picked two numbers. It certainly influences metabolic rates. It influences maybe stress at certain levels. But I would think I know there's a seasonal variation. I can look at the diurnal fluctuations, but wouldn't it just stay the same year after year? Well, it doesn't. There's a pretty big difference in the variation year to year at certain months when we have still quite a few fish around. So this may be influencing how the fish can perform, or maybe it's influencing when they migrate. Another thing, water surface elevation, it dramatically changes year to year. And so that's not something that we've accounted for in our density estimates. The amount of habitat that fish are experiencing can experience at a site year to year. And the last part is looking at the timing. So flow, here's our sort of average timing of fish in the bay. We have this bimodal curve of Chinook salmon out in Skagit Bay, and the early fish are fry migrants, and they just profile it with the flow records in the Skagit. You see this quite commonly with where the fry migrant peak coincides with the peak in Skagit River flow. And this is exactly what Martin said we shouldn't do. But anyway, so if you plot the week of the peak flow and the week of the peak fry migrants, you see a good relationship, as long as you throw out the two outliers, which I think I have a biological basis for doing that. These years, the population sizes were so low, we didn't really have many fry migrants. They just trickled out when they would. So so I think it's logical to throw them out. But what I want to point out is that I think we all know flows trigger migration. To the extent we can figure out how that's predictable, these migrations do definitely occur at different range of times. And so a fry migrant that comes out in February may be surviving much differently than fry migrants that come out in May. And if we can predict that, that may be useful. And then I guess my last slide, that's the results slide, just showing the preferences or there's two slides, one for salinity and one for temperature. And I think it's interesting that this is the frequency or the proportion of our observations, and there's hundreds to thousands even of observations of sampling for fish when fish occurred. So here's half the time we sampled in temperature from 0 to 4 degrees, half the time we caught Chinook, and so on and so forth. The fact that it changes in pocket estuaries takes a big dip when we get around between 8 and 10 degrees, and then starts to level out. It's interesting. The same thing in the delta. It's a little later, but it levels out. Well, these are the two habitats we postulated density dependence for, and we don't see that same thing in the offshore waters. So maybe there's something to that. We've seen fish experiencing pretty warm waters, and the salinity one's less interesting, but I just want to I think we should be monitoring the fish. I think we can do that better. I think we can be monitoring the fish food. And I think I've just added a few things to the list. I think we should be monitoring the environment within the estuaries in the ecosystem. And we're already out there. We can do that well. It's cheap to put loggers out. I think it's explaining more about the biology of the fish than what our current studies of just the life history types would do. And then just to be off the wall, I mean, I'm really looking for, it seems like the goal would be to have no marine survival ranges and what functions they are derived by. So that's it.
So we'll move to the discussion. So Martin and you come up.
Any other questions? Let's see. First, please. And Corey.
I thought those were all really good. My question is directed more towards Nate, but I thought Eric touched on it a bit. First of all, did you notice any influence of the Fraser River flow on conditions in Skagit Sound? And do you think maybe that might change in the future global warming scenarios? And secondly, the same sort of thing for wind. I think a lot of those models have an intensification of wind speeds, and then just the thoughts on what that might have on the ocean and perhaps even Skagit Sound conditions.
That's a good and sort of obvious question. We did not look at Fraser River influences, and that's something that seems like we really ought to do since it's the dominant source of fresh water. Although in much of the year, I think a lot of the Fraser flow will go in the direction of the wind. So typically in winter, it would be pushed northward. In summer, when you have those north wind days, more would flow out and around Vancouver Island. But we didn't do that. And in other things that I've looked at, there are some interesting trends in Fraser River flow that have to do with timing, right? This advanced snowmelt timing and river runoff in the Fraser is already documented, and that's also been documented in Puget Sound watershed. So that's one important change that's been unfolding in recent decades. And for wind, we tried to look at wind, but didn't actually find good wind records within the sound. So we haven't been able to incorporate in a lot of what we've done. And I'm not familiar with wind speed scenarios. It's another thing that I haven't looked at.
Good question for me. So thinking about your climate indicators and the structure of Greater Georgia, which you just found, what climate indicators and maybe their expression might be expected to be sort of similar system-wide versus very specific to different ocean applications or other local scales?
Could you repeat that question?
What indicators might you expect to be sort of global in nature, sort of similar across the sailor speed, and what would you expect to be more local indicators?
Yeah, so things that are probably common across the town would relate to the seasonal averages in atmospheric forcing. And so surface air temperature is an indicator that should be seasonally expressed across the town. Seasonal averages of precipitation and things like water year flow should be pretty well correlated across the whole town. The timing of those flows, though, is going to differ. And trends in timing changes will probably differ because of the different sensitivity of watershed. So, for instance, in a warming or in a warm year, the timing of flow through the Snoqualmie is not likely to change much at all. It's already rain dominant system. It won't be sensitive, but to see a big change in the Skagit or in the Tuala, the Snoqualmie system, where you've got a sensitive watershed with a big snowmelt component in cold years. So those would be sort of more local. Another probably global indicator was down, was probably related to inflows of oceanic water into the strait. And I was talking to Richard before this session began about it'd be great to develop some indicators for those deep source waters that are coming from the ocean side. But that is the dominant source of nutrients, and it also has an influence on things like pH, dissolved oxygen, and maybe the plankton community that gets flushed into the sound. So that might be another one.
Yes, maybe this is for Eric. Do you have an idea as to the relative amount of time that fries spend in the area you're looking at and the ultimate distribution of fry from that area? Because I think we see a fair amount, not fry, but we see a fair number, I think, through the Birmingham Bay area, and it would be different conditions if you're going north or going south for 50 days. Have you been able to make any use out of the models that they developed to move hardware?
So, we haven't really made use of the connectivity issue in a specific way beyond the study area that it shows, so within the immediate Skagit Bay area. We do have, and you're aware of this, spatial distribution based on genetics in the North Puget Sound. They're hitting that. I think you've seen, a lot of Skagit fish go north and out into the Rosario area, other San Juan, and then other populations, in different places. Not the dominant, a subnode is the dominance of Canadian fish in the north side of the state. But then to sort of touch on one other thing, the different life history types within the Skagit will see pretty dramatic differences in their distributions by fluid years. The flies sometimes can be 50% of the population in the bay, and sometimes 1 or 2%. And they go, they habitat differently than the other ecosystems. Does that help?
I have a question for Dave. Before we started today, and I were drinking coffee, we were talking about the fact that the trend we're seeing in Puget Sound surface water temperatures are that we're getting colder. Yet you showed a slide about sea surface temperatures that raise rock getting warmer. Can you help me understand that and then talk about the PDO signal on top of that trend and how it all works and where it might go?
Oh yeah, good question. So trends are time dependent. When you start and stop that calculation on a time series that has a lot of wiggles in it will end up having a big impact on what your trend is. So my comment about it getting colder in Puget Sound is if you start your trend line from 1980 to present, because we've had a recent state of years that have been cooler than that recent average. The 80s were really warm for the most part. 99 to 2001 or 2002 were some cool years, and then the last 4 years have been cool again. And this year is relatively cool in the Northeast Pacific and in Puget Sound. So that short period of the record is cool. An interesting observation is that while it's cool in that short-term context, it's not cool in the century-long context. And if you compare it to the 70s, it was colder in the early 70s. If you compare it to periods in the early 1900s from other data that predates the Race Rock series, you see that really the whole Northeast Pacific has had this kind of shared temperature history of Pretty cool in the late 1800s, early 1900s. A warming trend to the early 40s. A little bit of cooling for the next couple of decades with a few warm years in the late 50s, early 60s. And then quite cold in the late 50s, early 70s. Then warming, and now we're sort of on a little dip again. Part of it is CDO. Part of it is a circulation pattern that isn't a perfect match for the elution lower CDO. And there's a postdoc that I'm working with right now who's sort of redone the analysis that was used to develop that CDO pattern and index, but it's focused more in the Northeast Pacific, and it's a lot better indicator. Maybe this is, I've thought about putting this in my talk, but it was going to be too much material for what I had. But it's a better indicator for the Northeast Pacific influences on Puget Sound, and it captures a lot of this variability. Even the warming trend from 1910 to 1940 that is pretty striking for our part of the world, it's mostly due to changes in the wind field over the Northeast Pacific. And the cooling period is also mostly due to changes in the wind field over the Northeast Pacific. And now this recent cooling again, it's very regional. And if you compare what we've experienced in the last 20 years, going through a little bit of cooling with the rest of the world, we're an outlier. The rest of the world is still warming. Global warming hasn't gone away, but it's sort of giving us a break because our wind pattern is suppressing that effect. And that could last for a while. It could last for a few years, maybe a couple of decades, but it's not predictable. No one has shown an ability to predict how that will unfold more than about a year or two into the future.
So we're going to hear from, I have Henry and Richard and Pete for a few more questions, and then we need to be building a list of priority indicators. So if you're thinking about what you would put on your list of priority indicators.
Thank you. One of the things that I've been trying to understand on the home issues researching, especially productivity. We've been looking at the landscape change in the last 150 years. We considered our climate model about a decade ago. Looked at temperature changes, the rapid rate of the glacier melt, the change in shift in hydrology on the landscape for 150 years of land use. A couple of things that are kind of bouncing out over the last week as I've been here. One is the north winds, seems like we're getting stronger north winds and effects from that, as well as just a couple of weeks ago we had the first time I've ever seen a water funnel in Puget Sound, basically a tornado over the water, which is a real shift in thinking and then one other thing about the early need for planting by juveniles but before the wind speed and the wind direction and the time frame, to start looking at, if we focus on that as part of the issue, the other thing that I think we need to do fairly quickly is, by the end of this year, is have in mind a budget that we can put forward to start looking at how do we get better information over time to start making better calls on our management. But I do think that even by the end of this year, we should have something that we can start moving on in the monitoring and research. So we've got something that we can rely on at least bank on financially next year, and we have to start looking for the information.
And there's a bunch of discussion tomorrow.
Just to follow on to your question on regional forcing versus maybe some local things, I think that the biggest local thing I can imagine is land use changes and waterfront, real nearshore changes that influence individual stocks, and that the regional things then affect broad stock and broad species, but when you get down to local scales of the land use, and that goes all the way back up in the watershed. I mean, you get forestation changes or forestry changes way up in the spawning grounds that we typically have no control over, but it does impact the health of the rest of the livestock from that river. So local is more, I think, land-based, and then once they come out, the stocks mix and it comes back to the main discussion. These are all regional things that work in that direction.
Well, my comments about mostly between garden and nature is just looking at time lag and persistence of these different factors. So the climate factors propagate in the fusion track. And it takes time for the water to move in, and it takes time for the water to move out. It takes time for the system to respond. Also, the climate factors influence the fresh water and the flood frequency and the intensity and stuff like that. So one climate index could be relating to fresh water that makes the site survival or something else, as well as productivity and future sound. And so the question is, how do you unscramble all that?
I think one way that you could unscramble this is with the use of circulation models that are linked up with hydrologic inputs and atmospheric inputs driving it, and you have to have an ocean input as well. So you need to have those boundary conditions right, but the kind of circulation models that people like Parker and 3D are running or Mike Foreman, they use that information to force the model. And if you have some kind of biological module that gives you something about spring blooms or plankton cycles, you could probably identify different timing of events in different subbases and get a sense for some of the time lag. So there's definitely some interesting time lag from Puget Sound because the same kind of winter climate that puts a bunch of snow in the Skagit watershed is dumping rain down in Snoqualmie. And to the extent that that fresh water is stratifying the water column and making it suitable for a plankton bloom under the right weather conditions, it'll happen at different times in different basins. And there's a big lag between the delivery of fresh water in the Skagit compared to the delivery in the Snoqualmie or some of these other watersheds. So that's one of the lags. And then other lags have to do with the ocean signal. You get intense upwelling on the coast that's pumping up this high density, high nutrient water coming into the sound. It's not going to be expressed at the surface maybe for a month or a couple of months in some parts of the sound. So there's another sort of natural set of lags that will differ by subbasin. But I think you need a model to look at the processes and start to develop the kind of amount of information that you need to tie it down.
And you need to be a very spatial model too.
This question is for each of you. So thinking about your one of the interests, if you could target several variables you want to keep your eye on in terms of predicting Chinook data, soil data, chum data, for different stocks and different species. What would you be paying attention to?
I guess my interest is more is how you would, if you want,
how you sort of limit the number of variables you look at, or how you sort of aggregate those variables in a way that's going to help you avoid coming up with an exposed correlation. Also talked about
well, I think that the really big goals have to do with food web and the target fish themselves. That just seems like such a gaping set of holes in our understanding that we've got some long time series of physical variables already that we know are important parts of the system, either as drivers or sort of state variables like salinity and temperature. But trying to connect those directly to estimates for marine survival requires, probably Mars can do it. If we give it to Mars, he'll figure it out, but there's still this big holes in understanding about why the relationships exist. And I know that there's a need to increase the monitoring of sound. One of our frustrations in the work that we've been doing is we don't have a lot of long time series at particular places other than the lighthouse station. There are smatterings of data. Parker McCready showed some that he was able to cobble together from a few sites, data from the 50s and then data from the 80s and 90s. Nothing in between. So that is a real gap. Just trying to better understand some of the water column variations at a better time scale than one snapshot from stuff with the ecology data, right?
My answer would be sort of to be working in the small box that is fish going into the big box. and so working in the estuaries and shoreline areas, I think that we can do a better job of quantifying the abundance and condition of the fish that go through those habitats. And I think that measuring local environment is important for that. We've done a pretty good job of naming the fish into by system type, but that's probably not enough. And if we're not even measuring the fish between the fish, we absolutely have to be doing that. We have to do it by system type, so we have to know what the time and the size distributions are. To the extent local environments can change that, we should know how that works. It may be more of a research question sort of for that. If we find those functional relationships, temperature and salinity and different things, maybe it's not part of the long-term ecosystem indicators for harvest management, predictions for people. I think it's part of getting that input with small fish. I want to mention one additional thing. I think I mentioned earlier, there's some pretty big gaps in just our basic SAMA data. For example, some of the statements are pretty poor. But recently I've been looking at Chinook data and looking at like age structure. And even though it seems like assessment scales, I know it's not trivial, but would be a pretty basic thing. There's just huge gaps, and there's more of the exception to rule in its age structure for the important population. You have what you expect to have all the time.
Other thoughts on that? Yeah, I wanted to supplement some of what you were mentioning for freshwater processes, just because I had some additional thoughts there. The freshwater indicators that I would look at as related to survival within the system would include incubation flows as being particularly important for some pink and early life in Chinook, so fry migrants, species that migrate after immediate emergence from gravel. If we're looking at freshwater survival of yearling smolts, so the cohort steelhead that are emigrating after a year in freshwater, I would include rearing temperature and rearing flows as indicators. And then if we're looking at the timing of, which is also relevant potentially to survival in the marine environment, I would include incubation temperature as an indicator, as well as the flows during the out-migration. And then if we're looking between systems and trying to compare or extrapolate information to systems where we don't have snowpacks or have little information, I would include things like the gradient of that system and the amount of available marine habitat as it would relate to coho, steelhead, in particular. Add those against the freshwater indicator.
Great. Thanks. And I just want to, just a quick time check, we're about 5 minutes over here. Two more people will want to speak, and then we can break it off.
So we spent some time rummaging around and trying to deal with the lack of data, and I want to throw out a big idea, and probably we'll shoot it down quickly, but let's think about or entertain about entering having the geology paleo folks come in. Eric, you guys did an amazing study of coring down into Skagit Bay to look at the change of eelgrass and sediment delivery. I think that was George Pepper's work, right? Did you send you? Yeah. Anyway, so let's expand that on top of the Santa Barbara data that was done for anchovy and herring, which is a 3,000-year history, on top of the scale work that was done in Alaska, some of the Alaska sockeye lakes. So can we get the paleo folks looking at stuff that's drifted down into the anaerobic sections of Puget Sound to give us some kind of historical context of what those changes are, given that we don't have, reasonable data. I'd like to explore that and push that one back to the investigative session.
If you were going to try to
investigate issues like that in Puget Sound, you have a dead end. The reason is the sediments are not thick enough to preserve scales. These scales being shed by herring, for example. Salmon is not going to give you, you're not going to get anything from salmon. They don't shed scales. And so you would have to be focusing on organic matter, deposits, some other indicators of chemistry in the water, remains from foraminifera, plankton, right.
any of those would work.
The other problem you have is if you want to develop a chronology with a very high resolution, there is a problem with biomixing too of the sediments itself, so you tend to have near chronology, right? So you get in a way a moving average of, and you lose the very fine temporal resolution. Usually it makes sense.
I guess mine's probably a little bit more comments. I'm not specifically asking a question or continuing to be much. But when I think about some of these climate changes that we talked about in some of the freshwater environment, some of what we've seen with our spring Chinook, what you've got for the flows that these fish are coming into when they're spawning really affects the habitat type that they're spawning in. And so, as we talk about the summer being more sustained periods of lower flows, it really can affect the capacity of our basin. And I know that it goes much beyond even the spawning distribution, the rearing habitats for the longer, rearing fish as well. And there's just a lot to try to roll up with that, both with the winter flows, and that really brings in the physical habitat processes of wind, water, and sediment windows that come in, as well as the summer as well. And it's just a lot to roll up of those the changing environments on the freshwater side, as well as the estuarine and the marine. And when we get the forecasting and rolling all that together, it's not easy.
All right, I think it's time for lunch. Thank you all. Let's come back at 1 o'clock.